Okay, students, this is your 6.5 lesson, which is talking about one-to-one functions and inverse functions. We're going to just take it a step further with these one-to-one functions. So we're going to make a connection between the two. So the first thing I'd like you to take a look at on page 18, there are pictures of one-to-one functions and also functions that are not one-to-one. I would like you to make some observations. Go ahead and pause this and see if you can make any conclusions about these groups of graphs. All right, so a one-to-one function. Let A and B be in the domain of function f. If A is not the same as B, then f of A is not equal to f of B. So we have different inputs always result in different outputs. So we can write it that way. Different inputs always result in different outputs. So you already have examples of one-to-one and not one-to-one from the little graphs in the previous page here. So this would be one-to-one, something like this would be one-to-one. This would not be a one-to-one function. This would not be a one-to-one function. Something like this would not be a one-to-one function. So different inputs always result in different outputs. Let's think about this. These are two different inputs, right? But their outputs are exactly the same. So we're dealing with all things that are functions. We want to determine, is it one-to-one or not? So definitely keep this in your head here. Different inputs always result in different outputs. Okay. Now let's go ahead and talk about inverse functions. So now this is our definition here. If f and g are two functions such that f of g of x equals x, for every x in the domain of G. And now this is going to be the other direction. If I compose G of f of x, that would equal x for every x in the domain of f. Okay, if this is the case, then f and g are inverses of each other. Kind of a mouthful here. Okay, so we also want to take a look at the inverse, which could be written here as this. This is the inverse of f. Okay. All right, so a graph example of this. Let's first look at the table. So for the table, we want inputs and outputs. And we're going to switch them. So if x is 1, and let's say this is 3, 2, and 5, 3 and 7, 4, 9, 5, and 11. And then we have here 3 and 1, 5 and 2, 7, 3, 9, 4, and 11, 5. So that would just be switching those two around. Pardon me. So if we're looking at, the graph, so if we have tables, we're just switching the x and y values. Now, if we have a graph example, let's say y equals 2x plus 1. We'd go ahead and plot that, right? We'd go ahead and graph that. And so here would be that one, and I'm going to change colors here. And the inverse of this one, we would reflect over the line y equals x, but it would actually be y equals 1/2 x minus 1/2. And we'll get into how to find that if you don't remember. Down 1, right 2, or up 1, left 2. Okay, pretend like that goes through nicely. And then what we're looking for here is it's going to reflect across the line y equals x. Here is that they will reflect over the line y equals x. So for an equation example, we can say something like f of x equals x plus 3 over 5. The inverse of the function f would be 5x minus 3. And we'll talk about how to actually do those calculations, so don't worry here. And now we're going to prove that the following are inverses. So let's do f of the inverse of f. So I'm going to say, I'm going to plug in this 5x minus 3 in for x, and then add 3 and divide by 5. And that becomes 5x over 5, which is just x. So that is part of what we talked about up here, saying that when I compose them in both directions, we should get x. So let's try the other way. The inverse of the function f of x in this case, so the f of x is going to be the input, 5 times x plus 3 over 5, and then minus 3. Okay, so what happens here? The 5's cancel. We have x plus 3 minus 3, which is just x. So that is how you would prove that you indeed have inverses, is you would compose in both directions, and your result should be x for each. Okay, so this is inverse zone. It's on page, let's see here, 20 and 21. And we're going to go ahead and get started here with some of these examples. If you're feeling good about this and you feel like you want to go ahead and try this on your own, definitely do it and then check the answers with mine to make sure you're on the right track. But again, if you feel like, you know what, I've done this before, I know how to do this, please go ahead and give that a try. Okay, so first step is to find the inverse. That's actually all it's asking us to do. So I'm going to say x equals 3y plus 2 minus 4. So the first thing I did is I switch x with y. Okay, and now that next step is to solve for y. So I'm going to use my normal solving steps, and I'm going to multiply both sides by -4. So -4x equals 3y plus 2. I'll subtract 2, divide by 3. Let's clean that up a little bit. So -4/3 x minus 2/3 equals y. So this would be the inverse. So this is the same thing as the inverse of the function f. Okay, let's do the same thing with function g. So same steps here. We're going to go ahead and switch it. So instead of g of x, we'll write x equals y squared plus 2y plus 1. And our goal here is to go ahead and solve for y. So I see this, and obviously it's looking like, you know, we had a quadratic situation here, which we could see initially. So let's take a look here. Let me get my blue out. I'm going to go ahead and try to factor. And this is y plus 1 times itself. X equals y plus 1. We could write it quantity squared. And now I can take the square root of both sides. Don't forget plus or minus. And then I can subtract 1, so it's -1 plus or minus the square root of x equals y. And again, this is the inverse of function g. Okay, thinking about what the graph looks like, we know that this is a parabola and it opens up. That's g of x. The inverse, we have the square root function. So hopefully we remember that square root function is going to look like this for the positive and like that for the negative. So that is what it's going to look like there. And then h of x, let's go ahead and keep rolling. X equals y cubed plus 4. X minus 4 equals y cubed. And now I would go ahead and take the cube root of both sides. There is no plus or minus for an odd root when I take the odd root of both sides. Okay, I forgot to change colors. Oh well. So this is the inverse of function h. Okay, so if we think about this one, it's only going to give us part of this function. So if we're talking about the cube and then the cube root, we can definitely look at Desmos and kind of see what's going on with that. I'd encourage you to go ahead and plug that into Desmos to see what the graph looks like. Okay, so big idea. So this is saying from part 2's original functions, f, g, and h, which ones are 1 to 1? So in this case, which ones are 1 to 1? It's going to be, let's see here, f of x and h of x are both 1 to 1. Okay, so for these, if we're looking at the definition that we had talked about, those are the ones that are going to satisfy. So f of x and, whoopsies, and f of x are 1 to 1 functions. Okay, now of the inverses, which ones are functions? I wrote f of x and f of x. Oh my goodness. F of x and h of x, pardon me. Let's do that instead. Okay, so looking back again at the inverses, so we see the inverse of function f, g, and h. They want to know which ones of these are actually functions. And it's only that middle one that looks like that parabola that got tipped to the right. That's the only one that is not. So we would say here that, again, the inverse of f and the inverse of h are functions. So the connection between these two things is that if we have a function that is 1 to 1, function that is 1 to 1 has an inverse that is a function. So this could be a great way to be able to test out and find out which functions could be 1 to 1. So let's take a look at just 2 examples here, and then we can stop for now. Which ones are 1 to 1 functions? Show algebraically. So when it says this, it's fine to graph to get an idea and do a sanity check, but we want to actually do some algebra here and figure this out. So let's first specify where x is not equal to 0, because if x was 0, we'd have a problem in that denominator. Okay, so x equals 1 over y squared. So step 1, find the inverse. Okay, step 1, find the inverse. So we're going to solve for y. I would get y squared x. I'd multiply both sides by y squared. Y squared equals 1 over x. And then I take the square root, which would give me plus or minus the square root of 1 over x. So when I look at this plus or minus the square root, it's going to tell me I'm going to have some kind of action like this going on, right? Which is not a function. So this is our inverse. Okay, so that's the inverse. Since the inverse is not a function, k of x is not 1 to 1. Okay, so that's what we're looking at. The inverse was not a function, therefore this original is not 1 to 1. Okay, let's just try one more here. x equals the natural log of y minus 2. Now we're going to have to dig into chapter 5, unit 5, with our solving methods here. So we have the variable trapped inside of a logarithm. So we can exponentiate both sides. Okay, when I exponentiate both sides, I get e to the x equals y minus 2. And now I can add 2 to both sides. Now this is the inverse. Okay, this is m's inverse. So we want to know, is this a function? And this is, that if you were to graph e to, this is just an exponential, right? So an exponential curve, that certainly is a function. So we would say, since the inverse is a function, m of x, this original, again, we're always talking about that original, m of x is 1 to 1. Okay, we'll definitely practice more. Write down all the questions you have, and we will go through them together.